Hi students, today we'll discuss about Young's double slit experiment, which is a very important concept for your coming board exam, right? So in Young's double slit experiment, what we are taking, we are considering a monochromatic source of light, and at certain distance we are putting, that is very small distance, we are putting a rectangular, that is slits. Two slits will be there. Suppose one is your S1, another one is S2. The main source, this is your S. So when the light is coming from this point to this point, that will pass through the slits, and we are having a screen here which is at a distance of D apart. Suppose the slits, the difference between them is your D. This is the difference between the two slits, the distance, that is your D. So now you see, when the light ray is passing from the slits, suppose we are considering a point P here. So when the light is passing from the slit S1 and from the slits S2, and both are getting incident at a point P, so at that point we will have a interference. So in the interference we will be finding out what will be the resultant displacement of the waves, and due to that what will be the intensity, and how to find out the fringe width, what will be the different types of fringes that are produced from the center of the screen to that point, that we will be discussing. So here, as the wave is moving from S1 to P and S2 to P, so there will be a path difference and there will be a phase difference. So as earlier we already know the relation between the path difference is the phase difference, that you know, that is your phi is equal to 2 pi p upon lambda, right? So this is the difference and relationship between phase difference and the path difference. Here lambda is the wavelength. And also we know that when two lights are interfering at a particular point, then the resultant, that intensity, that will be equal to your I is equal to, you know, I1 plus I2 plus 2 I1 I2, that is cos phi. Here this will be the square root. So this part already we are knowing. And also from our previous discussions we know this, that maximum intensity, that will be at the point where the path difference will be n lambda, right? And similarly the intensity will be minimum when the path difference is 2n minus 1, this is lambda by 2. This part already we have covered in our previous discussions. So now you see, in this case, when the two lights are interfering at point P, so suppose this is the center, so this distance, this is your center of the screen. Now if we draw the parallel lines, so like this from the two slits, so you can see, let this is A point, this is your B point, and the distances from O to A, this will be your D by 2. Similarly from O to B, this will be D by 2, right? So here we will be finding out the path difference. Then we will put that relation to find out the point of maximum intensity and point of minimum intensity. The point of maximum intensity are known as your bright fringes, and the point of dark, that will be the minimum intensity regions. So now to find out the path difference between this S1P and S2P, you can say that we can take the right angle triangle concepts to find out the path difference. So now you see, suppose I am writing here S2P square minus S1P square. So this will be equal to, here you see, what is S2P square? This I can write S2B square and BP square, right? Similarly for S1P square, I can write S1A square plus AP square. So this will be your S2B square plus this will be BP square right? And similarly for S1P, I can write this will be your S1A square plus this will be AP square. Now putting the values here, what I will be getting? I will be getting S2B is your D. So this will be BP. What is your BP? BP will be your, you can see this will be your total distance. Suppose this path reference is your D. Total D, we can take this one as X. This path difference is suppose X, the distance between OP. Then OP plus OB. So this will be your X plus D by 2 whole square, right? Similarly, here we will be getting S1A square. S1A square is your D square. Then minus plus, this will be minus. Then what is AP? AP will be OP minus OA. So this will be your X minus D upon 2 whole square, right? So now you see here this will cancels out, so we'll be getting A plus B whole square minus A minus B whole square. So this will come as 4AB. So now this will be as 2XD, right? 2XD. Now you see here S2P square minus S1P square. I can write this one as your S2P plus S1P. Similarly, S2P minus S1P, that is A square minus B square. So this will be A plus B into A minus B. So here we are taking that this screen is placed very close. So we can consider here that S2P and S1P both are almost equal to the distance from the center of the screen to the center of the slit. So we can consider this one as D, this one as D. So this will come as 2D. So here we will be getting here S2P minus S1P will be equal to, this will be divided 2XD upon 2D. So here we will be getting, this is XD upon D, right? So this S2P minus S1P, this is your path difference. So this is a very easy derivation. So here we get the path difference will be XD upon D. So now you see, suppose this path difference, now we get your P is equal to XD upon D. So here you take, suppose we want to find out the point of bright fringes, that is the intensity is maximum. So we know for the intensity to be maximum, that P should be equal to N lambda. So we can equate this one, and these conditions are applied for bright fringes, that is their positions. So this we can get your P, that is N lambda is equal to XD upon D. So here we will be getting your X will be equal to N lambda D upon D. So this is the position of the bright fringes from the center of the screen where the maximum intensity takes place due to the interference of the light waves. So I think this is clear to you all. So from this derivation we can find out the positions of the first, second, third and consecutive fringes, right? So now you see here what will be the positions of the bright fringes, that is positions of bright fringes. So first bright fringe, suppose we are taking this one as X1. So your X1 will be equal to, we will put the value of N, that is 0. So this will be 0. So that means we can say at the center we will be getting the first bright fringe, right? Similarly for the second, suppose X2. So X2 will be equal to 1. So this will be lambda D upon D, right? And similarly for the third fringe we will be getting this one as lambda D upon, this will be 2. So this is 2D. So similarly we can find out the N fringes. So this will be lambda D, this we will be putting as N, right? So this will be N minus 1 into D. So these are the positions of bright fringes. Similarly we can find out the positions of the dark fringes where the intensity is minimum. So for the intensity to get minimum, we know P will be equal to 2N minus 1 lambda by 2. So here we can put this one as your, that is positions of dark fringes, positions of dark fringes, right? So here what we'll get, here P is equal to 2n minus 1 lambda by 2. Here we'll be considering this one as here xd upon d. So by cross multiplicating, we'll be getting x is equal to 2n minus 1. This will be lambda by 2. This will be capital D upon small d, right? So if we put the value, the positions of the dark fringes, suppose the positions of the first bright fringe. So positions of the first bright fringe, this will be equal to here, and we can put the value accordingly. So this will come as, here you put the value of as 1, 2, 3. So here we will be getting here positions of the first bright fringe, suppose at a distance of x1 dash. So this will be equal to n is equal to 1. So here we will be getting 2 into 1, that is 1, lambda by 2. So we will get lambda d upon d, 2d, right? So this is the position of the first dark fringe. Similarly, for second dark fringe, we can get this one will be equal to 2. So 2 to 4, so this will be 3 lambda by 2. So we will be getting 3 lambda d by 2d, right? Similarly, we can get the third dark fringe. So this will be equal to 5. So this will be 5 lambda d upon 2d, right? So similarly, we can get all the positions of the dark fringes. So in the question, it may ask that this distance between, suppose second bright fringe and the third dark fringe is so and so, then find out the derivation for the fringe, that what will be the lambda value, what will be the d value, whatever the unknown value we can calculate from this. So now another very important thing is that is fringe width. So we know what is fringe width. Fringe width is the distance between two consecutive dark fringes or two consecutive bright fringes. So here we will be getting your fringe width. Suppose we are considering the bright fringes. So this will be your x2 minus x1. So here if you put the value from the previous derivations, already we know the positions of the bright fringes, that is your here that we get at the center first one, and the second one is your lambda d by d, right? So by taking the difference, we will be getting lambda d by d, lambda d by d. So this will be your, so here we will be getting here that fringe width will be x2 minus x1. So this will be equal to lambda d upon d minus 0. So this will be lambda d by d. Similarly, we can find out for the fringe width of the dark fringes. So the dark fringes, you know what we have get. So we got this one as your dark fringes. So dark fringes is first one is your lambda d by 2d. Here 3 lambda d by 2d. So their difference we can find out here. So this will be equal to 3 lambda d by 2d minus this will be lambda d by 2d, right? So here we'll be getting 2d LCM. So this will be 3 lambda d minus this will be lambda d. So this is 2 lambda d upon d. So here we'll be getting here lambda d by d, right? So here we can observe the fringe width for the bright fringes and the dark fringes all will be the same. So this is the derivation for the width of the fringes between your consecutive dark and bright fringes. So from this topic you can get questions. Another thing is that if the total apparatus, total arrangement is placed in any medium where the refractive index will be different from the air, so you know for that case we have to modify all the formulas. So when the apparatus is kept or immersed in a liquid of refractive index something, then the wavelength will be modified, other parameters will remain same. So if it is immersed in a medium, in a liquid, then what will be the changes? The changes will be your lambda is going to change as lambda upon mu, where mu is the refractive index of this medium. So this is a very important concept. Sometimes in question it is asked, right? So we'll go for a question now. So now you see how to solve this question. Suppose we are getting this question. Now we see, in Young's double slit experiment, the width of fringes obtained with light of wavelength 6000 angstrom is 2 mm. Calculate fringe width if the entire apparatus is immersed in a liquid of refractive index 1.33. So this type of question sometimes asked. So you see here what are the given parameters. The wavelength is given as 6000 angstrom, and your that fringe width, that is your 2 mm. So this is beta is equal to 2 mm. Now other thing is given, it is immersed in a liquid of refractive index 1.33. So mu is equal to 1.33. So as we know, if the total Young's double slit experiment, that apparatus is immersed in a liquid, then your lambda is going to change. So here we will be getting your lambda dash will be equal to lambda upon mu. So this we can find out as 6000 upon mu. Mu is 1.33. So this is 4 by 3. So I can write this one as like this. So this will be 15. So this will be 4500 angstrom. Right? So now the new wavelength for the given experiment, this will be changed to 4500 angstrom. So we can find now the fringe width, this beta will be equal to, as we got earlier, this is lambda d by d. So by putting this value, you can find out, this will be, suppose now this lambda, you know, we can take the reciprocal, so that is be the ratio, so that it will be cot. So this will be lambda 1. Suppose this is your lambda 2 d by d. So this will come as beta 1 upon beta 2. So this will be equal to, you get this one as 6000. This is right. This will be 4500. So this cancels out. So this will be your 4. This is 3. So here we'll get, this is 2 mm. So your beta 2 will be equal to, this will be 2 mm. So this will be 3 by 4 into 2. So this will come as 1.5 mm. Right? So this will be your new fringe width when the total Young's double slit experiment is immersed in a liquid of refractive index 1.33. So I think this is clear to you all. Okay. This is very important for your exam point of view. Thank you.